Hello, everyone. Welcome to the second combustion webinar in the new year. Today, it's my great pleasure to introduce you our speaker, Dr. Lyle Pickett. Dr. Lyle Pickett is a senior scientist at Sandia National Lab, where he has been employed since 2000. His research expertise is in optical diagnostics of spray combustion in chambers that provides engine-relevant conditions such as high pressure and temperature. So he founded and leads an international experimental and modeling collaborative efforts to share spray combustion data sets online through the Engine Combustion Network, ECN. I think many of us are familiar with this, and encouraging the improvement of computational codes used to design and improve engines for increased efficiency and reduced emissions. With that, let's welcome Lyle. If you have any questions during the seminar, please type it in Q&A.
Which I've entitled Renewable Methanol Spray Combustion. And while I'm the presenter for this research, I'm really drawing on the work of a large number of people. Many of these people have participated very actively in the Engine Combustion Network. You may be familiar with our workshop. We do hold monthly web meetings and in-person workshops. And several of the people listed here have been major contributors and organizers on the topic of methanol spray combustion. So I'm going to be sharing some experimental and modeling research at Sandia, but also from a larger community. And calling out some of these people by name, Rafael Clemente is from Friedrich Alexander University in Erlangen, Germany, and did a research stay at Sandia and collected much of the data that you'll be seeing today. Paul Lien is at TU Darmstadt, is involved in CFD modeling and was a co-organizer with Rafael, I call him Rafa, on this methanol spray combustion topic. And Frederick Weissman is also a person involved in modeling from TU Vienna, was a major organizer for the combustion of and compression ignition topic on methanol spray combustion. And Julian Menin was the PI and lead for the collection of data on compression ignition of methanol, and then many other participants at Sandia. I want to thank those people, as well as acknowledgement for support by myself and others at Sandia Research. We are supported by the Department of Energy Vehicle Technologies program focused on decarbonization of off-road vehicles, Gurpreet Singh and Kevin Stork. And this, from a Sandia perspective, our approach is to perform experiments in a controlled way, spray and gas jet experiments. We use chambers that have well-controlled boundary conditions and are really designed to facilitate the improvement of CFD models. And through that experimental platform, as well as through the Engine Combustion Network, we have identified certain conditions, certain target conditions. One of those is featured here. It's we call it Spray A, and it was simply an agreed injector donated by Bosch, where we determined to operate that injector at the same conditions. So controlling the fuel conditions, injecting into ambient gas conditions at a certain pressure and temperature. If we could send this injector to many different institutions that were willing to participate, we could generate a very large data set. And so this is what the Engine Combustion Network has done. It now includes many different fuels. And so with prospects for focusing on low carbon fuels, low life cycle carbon fuels for the future, it certainly makes sense to continue to use some of this same hardware, some of the same experimental capability, and compare these newer fuels to those of perhaps those that have already been in the database. So I can recommend the Engine Combustion Network to you. I'll be speaking about it a lot since it's something that I feel pretty passionately about. And I can refer you to the website to find this data archive. It's there, and results are really prepared for ways to tailor towards CFD simulations. Just commenting a little bit more about some of the hardware. So we have had donations of fuel injectors that are suited for gasoline direct injection. With Delphi, and Delphi has now become Borg Warner, there's a new 8-hole fuel injector that Borg Warner donated, and this injector specifically has been chosen for studies of methanol, where the injection would be early during the intake cycle, where you're going to have a well-mixed or possibly stratified mixture at the time of ignition and combustion. We also have a single-hole version of that injector. And then we have these other single-hole nozzles. Spray A, Spray D has a larger nozzle size that, again, fits sort of the off-road heavy-duty space. And just speaking about the ECN and what I've described, what we're really trying to do is form a collaborative research group that can really benefit each other. And so we refer to ourselves as a peloton, as in cycling. And so the people that have gone on before and maybe have started some of this research, maybe have experimentally already investigated the topic, it really sets up a nice slipstream for others to follow, to join in quickly and to make an impact. This can be experimentally or computationally. And as we met for our most recent workshop, which was held in September in Naples, Italy, this is the slide that we shared. And I want to thank Alessandro Montanaro at CNR STEMS for hosting us at this workshop. I'm listing myself and 2 other organizers from the ECN, Gilles Bruneau and Ralph Hyrie, who've joined in this effort. And at this workshop, we have chosen, the Engine Combustion Network has changed, and we've chosen different topics for future research. All of these topics are focused on low life cycle carbon fuels. You can see the topic and then the leaders. So there is a very strong effort in hydrogen injection and combustion. There's methanol in the early direct injection application, and I mentioned those leads. There's really the space of these renewable fuels and compression ignition. And so we have active topics on OME, methanol, and renewable diesel fuels. Again, listing the leads on that. We have a really strong effort collectively on ammonia injection and combustion, led by Michele Battistoni and Jose Maria Garcia Oliver at CMT in Spain. And we also have a topic on battery safety and thermal runaway. So it's a very kind of wide variety of topics for the current research areas. And as we're in Naples, Italy, we could ask the question, well, how do these things sort of fit together? Why are we doing this research together? And is there even an overlap? And many of you know that Naples, Italy is the birthplace of pizza. So we say there that yes, there is a reason that this activity can fit together like a pizza, where we're combining sort of a perfect combination of ingredients, New World tomatoes with Old World cooked dough on a hot stone to create this kind of masterpiece. And so we can go further with this analogy and say, all right, if you really want to start a debate and people with a lot of passion and opinion, you would raise the question, who makes the best pizza in the world? And, you know, in our research community, it seems like there are these topics, and I can make a very strong argument for research in each of these topics. I will make an argument about methanol, research. But likewise, there's really strong reasons to look at hydrogen. There's strong reasons for batteries. Their high conversion efficiency, the opportunity to power our electrical grid through renewables. Very, very strong reasons to look at these things. And there are pros and cons of each of those. So there's strong reasons to look at OME, DME, and renewable diesel as well. So we view, speaking about the Engine Combustion Network, we view a lot of value in looking at all these things. And honestly, it's not clear to me that there is a clear winner. I think there's a strong reason to look at all these things together in some sort of combined pizza, if you will. So I'm just going to, as I go into this, I think my view of the research motivations has changed because I think that many of the challenges are about production, making of these fuels in high quantity, and it's not something that we can completely disconnect from how we plan to use it. So I'm just going to talk about those issues a little bit to motivate why methanol might be an interesting future. So one of the things to consider is the volumetric energy density. And methanol is a carbon-containing fuel. So this graph is separating those fuels or batteries that do not contain carbon or do not emitting carbon dioxide in the tailpipe. So it's quite interesting that even cryogenic hydrogen has a much lower energy density than does methanol, or than does any of the carbon-containing fuels. And of course, batteries are down here in terms of energy density, which is the significant challenge, especially for vehicles that are off-road or that are in remote places and so forth. So this is really a strong driver. I think we appreciate this and understand it, but stopping at a fuel that is very renewable in a life cycle basis, but that has high energy density is going to be a continual driver while this conversation goes on. And so I think it's important to consider an endpoint that with respect to producing methanol and these other fuels, what is the potential in terms of efficiency, in terms of course, cost will matter, and so forth, and in terms of things like land use and so forth. So a green methanol production is enticing because it really can scale directly with our ability to produce renewable electricity. And so I'm calling this slide favorable views on green methanol production because you will find different opinions in the literature. And so I'm listing the full sources here, but there are voices that say power to methanol efficiency can be 50 to 60%, even when using direct air capture for combining the hydrogen from electrolysis with the captured CO2. Even direct air capture, which is not a very efficient process, can, according to this study, could produce efficiencies that start to look pretty impressive. Now, of course, we should compare that to other sources. So here's a different source saying power to methanol efficiencies of 50% with production coming from wind and also using direct air capture. Other sources say 50 to 55%. Also state that methanol to gasoline efficiency, that is, if you can form methanol with such high efficiencies, so let's say 50%, what about producing an even higher energy density fuel, so a gasoline, that this conversion efficiency can be upwards of 93%. So, this starts to look quite promising for producing what we need, a high energy density fuel. But this is methanol, and it's got difficulties. It requires carbon dioxide in the process, a captured source of carbon dioxide, which is certainly a big challenge. So let's compare it to other viable alternatives like, oh, and before I go on, could mention that these efficiencies may increase if we could use biofuel processes with wise land and water use as well. But let's compare this to ammonia, since this is a carbon-free fluid, and there are projections that our efficiency in production from power to ammonia may be very high. 74%, these are not processes that are fully developed today, but um, I'm seeing numbers that look very impressive. And I think this is a really important thing to consider, that if ammonia can be produced with higher efficiency than methanol, for example, that in the end, it may be something that would take a greater hold. Now, there are other opinions about this. So 74% is maybe a future target, but other sources will say ammonia production to 60%, again, citing the assumption for how efficient the hydrogen production is. And this really, I think, illustrates the trade-offs then. So if we acknowledge that ammonia could be produced with higher efficiency, but then we consider how it's used, I'm going to rely on an analysis that was performed by Ishan Singh, who was a postdoctorate here at Sandia, and he considers separately, it's his own analysis drawing from other resources. He considers the prospects of producing these liquid fuels from renewables through electrolysis with a perhaps 70% efficiency, and then to produce 100 units of pure electricity down to this 70%. Now, through his analysis, he shows that you would have a higher conversion efficiency to produce ammonia than methanol, which again makes sense because you need to combine the hydrogen directly with CO2. But when considering how that methanol is used to produce power, we know that there are advantages for methanol compared to ammonia in terms of combustion. So the most striking thing would be if we look at the flame speeds for ammonia compared to methanol, that it's a factor of 10 lower for ammonia compared to methanol. And so there's high octane ratings for methanol. So there's a strong belief, and in practice, what we know thus far is that the efficiency to use methanol could be improved. So in the end, when you look at the overall efficiency through this process, we can have we start with 100 units, but we can get 20 out going through this methanol process. Whereas with ammonia, it's just perhaps marginally better. So the higher conversion efficiency with ammonia is offset by how it's used. Now, I understand that this is something that can be debated and so forth, but I think it is good for us to have a perspective on these different trade-offs that exist and seek the best solution in a fair and open way. So with that, I've made the case and given some trade-offs as to why methanol should be considered. And so let's go into this just in a little bit more detail. Its life cycle carbon intensity can be made very low. So if we're using renewable energy, if we're using biomass processes, if we're going power to methanol, we can definitely have carbon intensities that are less than 10% of that of regular fossil fuels. Another big advantage for methanol is that its storage, its handling, its safety is established. You'll find it all over. It's a major commodity for the chemical industry, and there is really a precedent for how to use it and store it, which is really not the case for um, other fuels that may have been chosen. One of those is OME. We don't have an infrastructure to move and transport OME, and that's a barrier for making a lot of it. There are large commitments, especially for marine applications. Maersk has ordered 1 million tons of methanol from a power to methanol, a green methanol process to power its 19 vessels. And it has already been implemented, methanol has already been implemented in heavy duty applications that involve direct injection during intake or compression. Usually this is done with a dual fuel situation. So you charge the engine with methanol and then use let's say a renewable diesel pilot to begin the combustion, but spark ignition is also been used. It has a high flame speed. I can say that we should mention that the entire racing industry has been using methanol for decades and has a lot of experience, enjoys the benefits of using methanol. So really, compared to ammonia and hydrogen, methanol has what you may consider as a sweet spot. It's a liquid energy carrier, has combustion and handling benefits. There's serious handling problems with ammonia as well. And here's citations for what I'm saying. But there are things that are problems. So with methanol, it's been cited that oil dilution, oil incompatibility is a concern. This means that methanol is penetrating and we're getting liquid wetting on surfaces where it gets into the oil. And through this, crankcase ventilation is required. Explosive mixtures can form in the crankcase, and that needs to be concerned. Related to all this is that methanol has a very high latent heat of vaporization. And liquid penetration, even though its boiling point temperature is very low, its measured liquid penetration can be on par with that of a diesel fuel, even injecting under diesel conditions. And it's safe to say that the way that methanol is introduced into the cylinder has not been optimized fully for either premix flame or compression ignition combustion. It's been used primarily in port fueling. There's strong potential to do more with this viable renewable fuel. Okay, and so with that kind of lengthy introduction, I am going to give a review of some of the things that we have observed about methanol spray combustion at ECN 9. And I, again, will be talking about two different cases. I will be referring to direct injection fueling during the intake cycle using this spray M, which is an 8-hole nozzle. Experimentally, we've been able to do some advanced measurements to quantify the liquid distribution. We've been able to study even impingement situations where it forms films and surface temperatures. So with apologies in talking about this at a combustion webinar, it's really the spray processes. Of course, there's going to be a direct connection to the combustion process if you have a film as opposed to a vaporized mixture in cylinder. But we'll be focusing a lot on those spray processes. And then part 2 is talking about methanol sprays with compression ignition. And here we've used one of the ECN injectors, spray D, which has a pretty large nozzle size. We're injecting at conditions where we would experience autoignition. We're comparing methanol to other renewable low carbon fuels like OMA 3 to 5 and dodecane, and applying some advanced laser diagnostics. I'm going to give a brief overview of some of the simulation capabilities that have been demonstrated at our workshops. And want to give full acknowledgement to the many people working on this topic, both on the experimental side and the simulation side. So the diagnostic that I'm going to show is one where we apply computed tomography of the spray. And so this is accomplished by mounting the fuel injector in a controlled chamber. We can change the pressure and temperature of the gases. We can change the pressure and temperature of the fuel injector, and we can rotate the fuel injector. We collect quantitative extinction imaging, high speed, of the spray. And then by rotating the fuel injector, it's possible to essentially do a CAT scan of the spray to render what the spray is doing in 3 dimensions. So here we're showing the 3-dimensional liquid volume fraction distribution. And with this injector, we can compare our result to that of a standard patternator measurement, where that patternator measurement would be performed, say, downstream at 50 millimeters away from the injector. And so our technique through computer tomography shows very good agreement. We see the spray, we see the plume, each of the plumes reaching the same target position, and so forth for this fuel injector. And so to gain an understanding for methanol performance, we can compare that. Again, we can build upon the data set and understanding that exists. One of those data sets has been developed for PACE 20, which is a 9-component gasoline surrogate. And now, as we go downstream into these different planes, so first I will say that we are doing this 3-dimensional computer tomography. We can choose to look at the data at different orientations. This is the ZY plane, and you're seeing the plumes on the top and the bottom, and we're injecting into a condition at 6 bar and 300 C. So now, instead of just looking at one of those planes or one of those plumes, we can make a more quantitative measurement by probing through the axis of the plume. So on the bottom here is radial distance from the center line of the injector axis, and we're comparing the methanol liquid volume distribution compared to that of PACE 20. Immediate observation is that there's a lot more liquid for methanol. It's easily 5 times higher. It shows similar characteristics as the regular gasoline, but much, much higher liquid, more persistence of liquid after the end of injection. And so this raises the question and challenge, how do you avoid liquid wetting on surfaces with methanol? And can CFD predict this? So let's go to some other conditions that are quite interesting. And instead of injecting at 6 bar, let's inject into a 0.5 bar condition where the fuel temperature can be changed, either 20 degrees C or 90 degrees C. And I'm showing experimental results for that. So with 20 C, we can see each of the plumes downstream at 25 millimeters, but with 90 C temperature, what we find is that the plumes start out at that location, but there's immediate collection of those plumes, and it leads to, in fact, a complete collapse. In rendering this in 3 dimensions, we found something pretty interesting. Stopping the movie here, we can identify each of the plumes when the temperature is 20 degrees C. It starts out where we would expect them to be coming from the hull. But at 90 degrees C fuel temperature, these plumes are already combining, and surprisingly, we can no longer recognize where the original plume was going. The place of highest liquid is actually at the interplume position. So the location that's exactly in the middle of those plumes is actually where there is the most liquid. There's some very interesting dynamics that create the fluid mechanics that produce such distributions. And we can resolve all these features in 3 dimensions with the measurement technique. So again, more quantitatively, it's interesting to look at the liquid distribution, both centered on the plume and at the bisection point between those plumes. data that can be used against CFD. All right, so why is the methanol penetrating so far, and why is it creating such an interesting dynamic at these conditions which are flash boiling? So this is not an easy thing to answer, but I think it is important to look at and develop some expectations for the liquid penetration based on two different reference points. So one point is to consider the pH phase diagram. That is, if I'm starting at 200 bar within the injector and I will inject into conditions in cylinder that have different pressures, I can address whether or not I'm injecting or expecting to reach a place where there is some vaporization. So if I inject into a 6 bar environment, I'm still in a liquid phase. I have not gone into a part of the phase diagram where there is vapor. We're showing methanol, isooctane, and pentane just as references compared to other fuels. If I inject essentially at conditions that are below about 3 bar, I am forming some vapor. I expect to have a vapor mixture already. And what's striking is the very extensive latent heat of vaporization for methanol, that it's necessary to have a lot more energy transfer. There's substantially more evaporative cooling for methanol than there are for these other reference hydrocarbons. And in this context, we can look at expectations for liquid vapor equilibrium or vapor liquid equilibrium mixtures at given mixture fractions. So now the liquid is mixing with gases that started out at some surrounding temperature. In this case, the gas at 0 mixture fraction, 0 liquid, was at 330 Kelvin. And so with all fuels, there's substantial vaporization cooling, reaching substantially cold temperatures. But with methanol, when we look at the fraction of liquid that exists at each of these conditions, so in the fuel, at a given mixture fraction, how much of the fuel is still in liquid form? And methanol has very long persistence, requiring mixing to very low mixture fractions before the liquid vaporizes. So these are the barriers. It's good to have this understanding about how methanol can be very different compared to the regular hydrocarbon fuels. And it explains the challenge of why the liquid really is going to penetrate so much farther at all conditions, at flash boiling conditions, as well as at conditions that aren't flash boiling. And compounded with this is the dynamic that was shown that the plumes are collecting together. Through the fluid mechanics, the plumes are not separate. They do not maintain the large degree of mixing, but will collapse into one very fuel-rich core, which also inhibits the vaporization. So these are all really strong issues to consider for the mixing of methanol. Now, as an outcome of this high liquid penetration, it's probable that films will be formed on surfaces. And so we have tried to investigate this outcome through a series of measurements. We've created a wall at a fixed position away from the injector. And this wall is one where we can control the temperature through internal circulation of the wall. And there's an optical section on one section of the wall to study films and film thickness. And there's also a probe to study surface temperature. Very thin, fast response thermocouples mounted in this probe, all controlled to the same temperature. And the idea is that one plume would strike, it's an 8-plume injector, one plume would strike the surface temperature probe, the other plume would strike this optical section, and we could perform these measurements simultaneously. And then the other innovation is that we have rotated the fuel injector, as has been done for the computed tomography experiment, such that we get film and surface temperature measurements at different impact positions for the fuel injector. And so I'd like to share some of those results here, where the fuel injector temperature, the gas temperature, and the wall temperature have all been controlled to the designated temperature shown. So at lower temperatures, what happens with the double injection event is that there is cooling at the point of, at the impact position, and that cooling substantially increases when the temperature of the fuel goes up. There's more evaporation cooling. And when we go to the 90C condition, what's interesting is that we're seeing the outcome of the plume movement going towards the center. And so the place of highest cooling is actually in a different spot for each of these temperature conditions. And it's really more towards the center, and it doesn't reach this sort of fixed probe position as shown. So these are all really valuable data sets that can be used for evaluation of CFD. And I want to just briefly give some of these CFD results that have been shown at ECN 9. These were different groups that submitted those results. I don't really have time to go into the details of what they're doing. But one of the challenging conditions is this flash boiling condition, where the fuel is heated to 90C, and we observe this collapse together of all the plumes. We can ask, how does CFD do in predicting this plume collapse? And when we identify the plume position relative to the center line, and just look at the data quickly, we find that the group that has the best prediction is University of Aquila. They are able to see more of the plume collapse than the other CFD simulations, showing the videos of this process where we go through the plume center. We find that, again, with the method that University of Aquila is doing, there is more of a tracking and a motion of this liquid volume fraction compared to the other groups. And so this raises the question, what exactly are they doing? They have implemented some very clever breakup models for the spray that includes detailed analysis of bubbles forming in a flash boiling scenario, how those bubbles would form and spread and break up the spray. And this shows it's a promising direction. It's a challenging problem, but the technique is reflecting more of the physics. Okay, so along with those simulation results, we have simulation results showing the cooling of the spray, as well as the predicted wall wetting and surface temperature. And the evaluation here is that the physics of this look quite interesting. There are some discrepancies. The experiment is showing a cold center, but the simulation is showing a still hot center related to the liquid film. So again, this is something to work on. And now, in order to give some effort in this presentation towards combustion, I'd like to then focus on some outcomes for methanol combustion. And these are conditions at very high pressures. So we're injecting into pressures that are above 60 bar at elevated temperatures. And we have a collection of both experimental and simulation results. Now, methanol has a very low cetane number, a very high octane number. And so it experiences very long ignition delays. It's possible to ignite the fuel spray at these conditions by achieving very high temperatures. Really, the temperature needs to be above 1100 Kelvin. And so this will require very high temperature gases created with a pilot, created with high compression ratio, created with high preheating in order to achieve ignition. So we can compare that to OME 3.5 versus dodecane. Interestingly, when we attempted to measure soot for methanol, as well as OME 3.5, we found that there was absolutely zero soot formed. This is an extinction imaging technique. One can see the liquid, and usually we would find soot forming and extinction from soot, as we see with dodecane. We have observed soot with highly oxygenated fuels, but honestly, this is the first time that we have observed completely zero soot, despite the fact that we're operating at very high temperatures, despite the fact that there is very rich combustion, and we're using heavy EGR. There is no soot formed for methanol or OME 3.5. We think that there's reasons for this related to the fuel chemical structure and such high oxygen weight percents. We observe no soot and no soot trade-off when operating with high EGR to simultaneously reduce flame temperature. We've performed a series of detailed measurements on the cool flame distribution, comparing OME, dodecane, and methanol. And here we are at an elevated temperature as necessary for methanol. We do find cool flame formaldehyde upstream of the location of high temperature reaction in all cases. We can also compare measured OH chemiluminescence for methanol, OME, which have very similar ignition locations and liftoff behaviors, whereas methanol, even at 1100 Kelvin, is producing ignition and liftoff positions that are much farther downstream. A lot more mixing is occurring for methanol spray compared to these other injections. And we thought it would be interesting to combine the diagnostics where we have planar laser-induced fluorescence of formaldehyde that's overlaid with OH chemiluminescence. So you can see that there's a lot more formaldehyde that is forming upstream of the high temperature reaction zone for these more reactive fuels, but with methanol, there's more of an overlap in where the formaldehyde is forming and the high temperature flame takes over. So again, these are really some opportunities for a detailed model evaluation. Now, liquid penetration at these conditions, once again, we see long liquid penetration for methanol compared to the other fuels. And so we need to consider that the highly evaporative methanol, along with its longer liquid, it's going to tend to penetrate farther and could affect the flame structure downstream. Some quick comparisons towards CFD. So in this case, we're looking at predictions of the formaldehyde distribution against the measurements. And so roughly speaking, here's a simulation from Technical University of Denmark, showing the consumption of formaldehyde in the same vicinity as what we see experimentally. That consumption of formaldehyde and the existence of the high temperature flame is occurring at about 40 millimeters downstream. Likewise, with an OME3 prediction, we're finding pretty good agreement in where that formaldehyde is formed. These are all, there's many things that are happening here to make such a comparison, details of the spray model, as well as the chemistry used. And with apologies, my computer's a little bit slow in responding. Okay, here it goes. We can also look at the predictions at higher temperatures with methanol and with OME3. You will find some discrepancies. So in this case, the consumption of formaldehyde is a little bit earlier, more advanced for the simulation at Sandia. And that's true with the OME 3 to 5. We have a prediction of formaldehyde that's a little bit longer than what we see experimentally. And so these are again things to work on for the future. So in summary, we've embarked on studies of renewable methanol spray combustion, as well as other low life cycle carbon fuels. All this is happening through the Engine Combustion Network. And there are specific things that are challenge for CFD. We can identify the flash boiling behavior, the plume interaction and collapse, the extensive liquid penetration and film formation and surface heat transfer that's observed. And this is just sort of a general result independent of reaction and combustion. Under combustion and compression ignition conditions, we find that methanol burns well, but it does require a very high temperature ignition source. And it produces soot-free and low temperature combustion, which again is a great opportunity to capitalize on both the soot-free as well as low flame temperatures where presumably nitrogen oxide formation would be low. So the prediction of these things in detail, the spray evaporation process, the low temperature combustion process, the high temperature flame stabilization, all these things are ongoing. And I could just say, please join. If you'd like to join in the ECN Peloton in simulating these conditions, in performing experiments at these conditions, you're more than welcome to do so and could refer you to the website. So with that, I will thank you all for listening to our research on renewable methanol spray combustion, and I'll be happy to take any questions